So that is the battery sizing calculation. Again, the question. So you selected the battery. So what is the voltage of that battery? The voltage of the battery, you can choose whether it's a 110 volts or 220 volts. Suppose if you are choosing a 220 volts battery, then generally you cannot find what is a battery. Battery is a number of cells, right? Combination number of cells which are connected. So now if you are selecting a battery, in that we can find so many cells. So you have to decide the cell voltage. Suppose the cell voltage is 2 volts. Then nearly I required 110 number of cells which are connecting on the series. Then the voltage will be add up. That gives me a 220 volts battery. So you can decide what battery you want, 220 volts battery or 100 volts battery. Even we are using for our telecommunication purpose, we are using 48 volts battery also. So it totally depends upon your requirement, whether 220 volts, 110 volts or 48 volts. 48 volts generally for PLCC communications or OPD, FOTE communications, dedicated that is. And for 220 kVs, 220 volts battery is the widely used for all across all the substations. Again, so this is just a fundamental kind of selecting the battery. But if you just look into the sizing that we are doing as per the IEEE 485, it says that the battery voltage, a number of cells shall be selected, depends upon, it is depending upon that what is the maximum voltage that battery has to feed. You can think of that, suppose a battery having, has to supply the voltage of 220 volts plus 10%. It's a general thing, right? You're allowing the voltage variation plus or minus 10%. If it is plus 10%, 220 plus 10%, 242. The battery has to supposed to feed that 242 volts. If so, 242 by 2 number of cells, then it's coming to 112 number of cells. 2 volts per cell, 112 number of cells. Again, if I am placing 112 number of cells, during the low discharge, during the less voltage, like minus 10% of the 220 volts, which is 190 volts, then the battery may getting discharge from each of the cell could be comes to like 1.85. So that is the end cell voltage where we have to again check some condition. Let me show that in a practical way. Then you can able to understand the concept behind this. So let's wait for a minute. I just want to bring up this. Yeah, team able to see the screen, the battery one, the calculation sheet. Yeah. So team, you can see here, here just this is my input calculation. I'm sharing this calculation. You can feel free to play with this. This is the type of the battery, which is VRLA battery. The manufacturer is could be a Exide battery or equivalent Amaron battery, whatever you want. So 220 volts is my nominal system voltage. Maximum system voltage is 220 volts plus 10%. Minimum system voltage is 220 volts minus 10%. Nominal cell voltage, each cell voltage is 2 volts. End cell voltage is 1.85 volts. The end cell voltage is that what is the minimum voltage that battery can give before going into the discharge, pure discharge. Once the battery is below this, then the battery cannot be charged again. And the float voltage is 2.23 volts, where this is the voltage that we are providing to the cell to make the battery in the charged condition. It's like a tickle charging condition. And a boost voltage is a voltage generally we are again applying to the cell to suppose if the battery was drained, suppose for 50%. If I want to charge the battery fast, so boost charging. So that's a boost voltage. And minimum site ambient temperature is -5 degrees. Temperature correction factor is 1.18. This is the manufacturer one. Aging factor is 1.25 as per the standard. Design margin 1.15. Now, first of all, I am calculating the cells, number of the cells required for my 220 volts battery setup. So the nominal cell voltage is 2 volts per cell. The battery voltage is 220 volts. then the cell float voltage is 2.23, where this I got from the manufacturer. All these relays I'm getting from the manufacturer team. Now, what is allowable voltage? I said 220 plus or minus 10%. 10%, 242, minus 10%, 198. So what is the maximum number of cells equal to? Maximum system voltage by number of, by the cell voltage, nominal voltage, right? So what is this maximum system voltage? You can see here E43, where what is this? This 242 by E40, which is cell float voltage 2.23. So this giving you 108.52. So I am rounding it off to 110 numbers. Now, if I'm selecting 110 numbers, then let's see. End of the discharge cell voltage equal to minimum system voltage by number of cells. 198 by 110, 1.82. 1.82 is the end of the discharge cell voltage, where I selected the cell voltage is 1.85, which is more. It's good. Next, I am preparing. I'm considering. I'm preparing the load schedule. So for where we have to do this, then again we'll come back to that. So these are all my DC loads for my substation team. You can see generally the DC loads in the substation, as I said before also, it's only the control and relay panel. So this is my 220 kV control and relay panel, where in this control and relay panel, we are having these number of relays and master trip relay, supervision, all these things. So for this, these relays, the first 4 relays, sorry, Tim. The first 4 relays are require a continuous supply. And when a fault occurs, then the master trip relay and local trip relay will operate. So you can see these are the momentary loads or intermittent loads, which there be only for 1 minute, less than 1 minute. And these again the continuous loads. So from this each 220 kV line panel, I can conclude that 176 watts is my the continuous load and 12.6 watts is my momentary load. Suppose if you are having 2 number of panels, then 2 into 176 is your continuous load from the 2 number of this, and 12.6 into 2 is that. Fine. And the next come to the 220 kV bus coupler protection panel. In the bus coupler protection panel, we are having a BCPU where 50 watts, trip circuit supervision relay. Again, 3.3 is a continuous, master trip relay non-continuous, so on. So 220 kV bus coupler required 82 watts of continuous and 6.6 watts of momentary. How many bus coupler panels we are having? Only one, right? Only one bus coupler. So one. And single bus bar and double bus bar protection panel, tiebreaker protection panel, transformer panel, single. You can see the breaker, closing and tripping coils. There is no for the motor team. Motor is AC. This is a DC part. And 33 kV transformer, 33 kV feeder, 33 kV bus section, 33 kV breakers, and the SAS. Some lights, miscellaneous, inverters, whatever required. Okay. So these are all my loads. So when I am done with these loads, then I am preparing a load cycle. I am preparing a load cycle where you can see that I'm considering that 0 to 119 minutes it's feeding continuous loads. The continuous loads will be common for all, you can see. So the continuous loads will be there from 0th minute to 180th minute, 3 hours. But in the 119th minute, there is some momentary loads which are required, which are tripping my breaker. That is my operation of my double bus bar protection.